Thanks. Well, welcome back, everyone. We're now finally on week number 4. After this week, we're at the 25% mark, so we're definitely getting through it. And it's a pivotal week since when we return on Tuesday, we'll be doing our first exam. And that's all we're going to be doing on Tuesday. It's going to be a 75-minute exam. I'm really going to rate it for a length of about 60 minutes. So think of the extra 15 minutes as kind of fluff, but also to check your work, those kind of matters. So don't forget, the sample exam 1 problems are listed here. These are directly from the text. I'm thinking about putting an extra resource as well. So see something below here soon before Thursday's class that says sample exam 1 problems version 2 is all it'll say. Our exam is only going to be over these sections here all the way to 3.7. And when it comes to 3.7, the due date is listed at September 16th, which feels pretty aggressive. I just have to put a date in there some way, somehow for the system to accept it. But keep in mind, due dates are only for pacing, nothing else. And once we come to Friday of this week, we're considered pretty much full on in review mode, getting ready for the exam. I'm going to unlock the due dates of all these sections to be pushed to September 19th, the day of the exam. So that way you can go back into the system and work those problems. So pretty much the way I'd probably study for this class is definitely get those homework problems settled out, then start taking a look at some review problems here. The next set I'll have posted there, and that would be a good itinerary to start out with the studying. Also, keep in mind for the exam, I'll probably mention this a bunch of times since it's just our first one coming up. It is closed book and closed notes, but you're welcome to have a scientific calculator. The only thing about your calculator is it can't be an app on a cell phone. It can't connect to the internet. It can't be a graphing calculator, and it definitely can't say CAS on it, computer algebra system. So as long as it's a basic graphing calculator, these are the 2 typical examples, I'll be happy with it. If you're not sure if yours qualifies or not, either show me after class, take a picture of it, or send me an email with your model number, and I can check that out for you right away. Well, other questions at the moment, folks? Okay, give me 1 moment. Oh, thanks. Also, we have our quiz due today. I forgot about that. And I'll be posting another quiz on this week. It will be due on Tuesday, but think of it as kind of a big hint this time. A quiz that goes from this week to be due on an exam day. It's going to be a question very similar to a real exam question. My next quiz will be based off 3.7. If you can get through that problem and solve the quiz, you're in pretty good shape for that type of problem on the upcoming exam 1. So if you get stuck on that question, reach out to fellow students, reach out to me or anyone that helps you study for these, and make sure you've got that next 4th quiz down pat, and you'll be in great shape. So that's our plan going forward for the rest of this week and our upcoming exam 1. Any questions at all, folks, about any of those announcements? Okay, well, let's get on with our work so far. Before we jump into section 3.5, we have a question from the class on something out of ALEKS. I believe this one is based off section 3.4, composition of functions. And not all of those are as easy as the others, especially when I see something that says domain of the composition f of g. To me, that's actually the tricky part, anything involving domains. So if you're losing points here and Alex is being kind of bully, sorry about that. I'll be very happy to help out with any questions that come up along those lines. But on exam 1, I'm not going to be as demanding on domains as this. It's going to come up here and there, but not necessarily after you do a complicated composition or things like that. That is definitely quite a bit harder. Well, let's give this a try. There's 2 functions indicated. You know, it might work better if we just take this and throw it right into the notes right here and now. Okay, so our work on this problem is going to be in the section 3.5 notes. That needs to be blown way up now. Things always paste a little bit funny. Okay, so we've got two functions of f of x and g of x. I'll let f of x be in blue and g of x be in green. First thing we want to do is that composition, f of g of x. So whenever you see f of g, I mean, that's tricky already because that's just the name of the new function, the composition. And when you evaluate it at x, you have to know this formula. So this is essentially what they're asking us to do. We need to take f, because it's the outer function that came first, compose it with the inner function g because it came second, and it will look like this. So that part is the actual formula in the process. And from here on out, it's just a bunch of substitutions. Some people skip some steps here. If the way the composition works is clear in your mind, you are absolutely welcome to do so. If it's a little bit tricky, it's good to go slowly and methodically. That's how I'm going to do this one. I'll just copy the f, open a parenthesis to show what the input is. Now go to g of x and make this substitution. It's 7 divided by x plus 1. Then close a parenthesis. And now we make a second substitution after this step. But does that make sense to folks to this stage? Okay, so I replaced what the g function was. Now this next substitution always looks weird. What I'm doing is looking up f. There it is. I'm going to write it down, but anywhere x appears, just put a big container for where the input is going to go. So the f function goes 5 divided by x plus 2. So that's our setup so far. Then next substitution, 7 divided by x plus 1 goes right where that x was for the f function. So 7 divided by x plus 2 would go right there in that location. Well, we got through the composition. Now we have to simplify that. It says simplify your answer as much as possible. And the only issue here is we have a fraction in the denominator of the fraction. Yes, question first?
Shouldn't it be 7 over x plus 1?
Oh, that was a big mistake right there. Thanks for spotting that. I'm going to put here, I mean, because the exam is coming, suppose this was your problem and it was 5 points. This is what I would have done. Oh, I wouldn't erase anything on your exam. That's rude. I would have done this, and you might have lost something like just a point or something like that. So if there's a small error like I just made right there, that's not going to make or break you in the algebra. As long as the rest of the process looks correct, then you're still in good shape. But thanks for spotting that. Let's put in the real value of 1. And now we can maneuver through this a little bit better and start cleaning it up. Other questions so far? Okay, I would say the first thing to know is these parentheses here are not completely necessary. I only put them in to be careful with the composition. Now to simplify it, it's all going to be based off that denominator. I want to eliminate that right away. So I'm going to put a grouping symbol around the whole denominator here. A new fraction, let's give this a color that stands out. And go to that denominator highlighted in yellow, multiply by x plus 1 over x plus 1. So what this will do is, well, when it distributes into the numerator, nothing too fancy. We'll just have to distribute 5 through. Well, when the x plus 1 distributes into the denominator, here to here is a cancellation. You'll just get 7 out of that because the x plus 1 down below and this factor, they're just going to wipe each other out. So this is about the fastest way to simplify this function that we have. And here's what the next step will look like. First, across numerators, it's 5 times x plus 1. Then in the denominator, let me show those arrows again. This goes here to here, and we just pick up a 7, nothing else. The sign in the middle is plus. Let me multiply here to here through the distributive law. So it'll be 2 times that x plus 1. So this one's still not simplified, but it's definitely better because it's an ordinary fraction, not a complex one. And to me, that's probably the nastiest thing about dealing with 2 rational functions at once. You just have to get through this at some way, shape, or form. Any questions at all, folks, to that stage? Okay, let's do our final cleanup of this thing. In the numerator, it's completely your choice if you want to leave it factored or distribute the 5 through. If you distribute it through, you'd get a 5x plus 5. If you left it alone, then just don't forget the parentheses to get the right answer in Alex. Down below, we really do have to distribute because there's like terms. When we take 7 plus 2x plus 2, we did have to combine that denominator. So finally, when it's all said and done, we have 5x plus 5 over 7, let me try again, 9 plus 2x. Or 2x plus 9 if you prefer. So that's what's going to go right inside here. We'll have 5x plus 5 divide by 9 plus 2x. But now this is the last thing we have to sort out. We still need to know what is the domain of f of g. So I'd say this is the harder question by far. Let's do this one really carefully. Any questions at all so far? Okay, there's two issues that come up whenever you're doing domain and the problem happened to be a function composition. The first thing we look at is we need to know what is the domain of g of x, because that's the first thing going inside f itself. So I can't pick a value of x. It'll cause a division by 0 right there. I want to see what the excluded value would be for that function g. Exactly, because it's 7 divided by x plus 1. Let me zoom back in there. You can't put a -1 inside the g function. So we can start next by saying for domain, I'll keep this color coded still to say what came from where. X cannot be equal to -1, and that came from the g function right here. Now we have to look at this one. I'll keep this in black. And here's the second matter. We couldn't put a value of x that caused 0 down in there, but we can't put a value of x inside g such that we run through the whole composition and end up right here in the answer. You can't divide by 0 here either. So we have to take 9 plus 2x, set that one equal to 0, and that's our second excluded value coming into this problem. So we can subtract 9, divide by 2, and now we can say x also cannot be equal to -9/2. Let me put just a little arrow here to indicate where that second value came from. So when we put those two together, finally the domain in interval notation would look like this. I'll go from, let's see, that's about -4.5. So that's the first problem we hit. -infinity to -9/2. Union, -9/2, up to the next problem point, right here at -1. Then union from -1 up to positive infinity would be our full answer on this one here. So that's the whole process. Again, these can be pretty tricky, so be careful with the composition, but the real issue is for domain, step 1, finding excluded values there, and then step 2. Oh, that's really weird how that draws. We have to find the excluded value from the end result. Well, we did it, folks. That's probably one of the nastier problems in that whole set, Alex. So thanks for bringing that one to our attention. Other questions at all on running through this composition? Okay, well, we did it. I guess I would say also, this is probably another major trick on this problem, just cleaning up the fraction by multiplying above and below by the least common denominator. Well, let's take a look at some more issues on these notes. But first, what we've been doing so far in this section was looking at transformations of functions. We went through the list of these various transformations we saw here. But after we got through all that kind of stuff, the good news is the rest of the notes are not as bad. We're going to be dealing with the so-called even functions and odd functions. We'll look at a test to determine if a function is even or odd. And that's what's going to finish off these notes for this section 3.5. We'll next start 3.7. We'll probably finish it a little bit earlier on Thursday's class. So if you have problems you'd like to bring to class for kind of an impromptu review at the end of 3.7, then I'll be happy to take a look at those as well. First, let's take a look at the issues here with even versus odd functions. An even function is a function such that, well, here's the equation, f of x has to always be equal to f of -x in the domain of f. And the major issue here is, if you can have that happen, you have symmetry with respect to the y-axis. So these are all one and the same. If you know your function's symmetric about the y-axis, it's an even function, which would imply that equation f of x equals f of negative x absolutely holds. Now let's pause here on the definition and let's take a look at some even functions. Here's a whole bunch of functions we have here, but as long as there's symmetry about the y-axis, that function will be even. So let's go down the line. Here, if we flip across the y-axis, let me see what's wrong here. Oh, I can't draw if I have the table selected. If we flip around like this part of the curve will overlap with that part of the curve, so it would absolutely be an even function. So we can say on this one, it's even. This one would be even as well because of the same symmetry, but this one is not going to hold. If we reflect just across the y-axis, we would get to this part overlapping and this part overlapping, but that's a whole different kind of curve if we do that sort of reflection. So that one is not an even function, but this one would be not an even function. I almost made a mistake there. Same issue as over here. And well, this one is neither even nor odd. Finally, getting to this one, we have even. So they gave us 3 even functions on this whole list. Does that make sense to folks on how to spot them just visually? Okay, so the short of it is, if you have an even function, you should be able to fold your paper across the y-axis, and your curve is going to overlap on top of itself. So that's the visual test for even. The trouble with that is, we go back to our formulas, we may not always have a graph. So if we have something like an example 6, where it's just a function, I mean, you can graph it, no one's going to stop you. But if this was a problem in an exam setting, we would need this equation right here to determine the function is even. So before we try example 6, let's do our own example. Let's make a function go like this. I'm going to borrow one of the functions from the very top, y equals x squared. That function will be plotted in this way. And if we say y equals x squared, keep in mind y is always equal to f of x. So then if we try out the equation right here, f of x, that's the left-hand side. The right-hand side says also evaluate f of negative x. So f of negative x would be equal to, and honestly, that's a tricky composition already. It is a real and honest function composition because what's going inside f is not just x. It's negative x, a brand new function. So right where you have your x squared, you have to put in a parentheses like before. It's been raised to power 2. And negative x goes inside just like that. Now, the way the parentheses were formed was absolutely vital because we wrote just that. Well, that's negative x squared, and it does not simplify. But if it's written this way, as it should be, let me try again. Then this would simplify. Negative x times negative x is positive x squared. So this alone shows f is even because we just demonstrated that this portion does hold. We got x squared both times. Well, taking a look at this, it's not a coincidence I used a power 2 there. 2 is even. And if you just have a variable raised to a power, that power has to be 2, 4, 6, 8, and so on to get an even function out. So that's definitely a nice hint on these kinds of problems. Likewise, for odd functions, we can just switch this up to y equals x cubed. 3 is odd, so it automatically gives you an odd function. Before we try that next portion out, any questions so far? Okay, so here's the main takeaway for odd function. We'll have an odd function if that new equation holds, almost the same as this one, except there is one extra negative sign in front of the function here on the right-hand side. But we'll also know that the graph of an odd function has symmetry with respect to origin. That's a weird statement, but here's the gist of it. If you say symmetry with respect to y-axis, then that means the y-axis or any point on it never moves when you do a fold across the y-axis. If you have symmetry with respect to the origin, let's go to the top of the notes. there's two folds on your paper that has to happen. Now here's what it would look like. Turns out this function right here is an odd function. We expect it because the power is 3 for cubing, so we expect odd. But what about symmetry with respect to the origin? It's two flips. First, fold the entire curve about the y-axis. If you did that, this portion right here that I'm drawing over would emerge into this location. And this portion right here on the right would emerge in that location. That's one reflection that we reflect a second time, this time about the x-axis, so going this way. The only thing that doesn't move is the point right in here, right in the origin. So that's why we call it symmetry about the origin. So take this dashed line, do one more fold. We're going from the bottom to the top, reflecting across the x-axis. This line here that I'm filling in, if you reflected it, would just become the original back up here that I'm drawing over again. Likewise, this line, fold your paper across the x-axis and reflect, becomes that line. So all of this tells us finally, after two reflections, across the y-axis this way, across the x-axis that way, you just get back the whole original curve. That means it must have been an odd function to begin with. Same kind of issue here. Reflect across y-axis, across x-axis, you just have the original curve, so this one's odd. But these two, or this one right here, is the only one that doesn't fit anything. It's neither odd nor even. It doesn't have symmetry about the y-axis or the origin. So those are pretty much what can happen visually with even and odd functions. I like looking at graphs to sort all this out because it's really pretty quick once you look at the trick. But again, our goal is to find if functions are even based off that form right there. And so we also have to pay attention to that formula right here on this equation. So let's give this a try, starting off with, let's go with the cubic function again. So this is y equals x cubed. It starts off by going up, almost like a parabola, except it's steeper this time, much more steep. And on the left-hand side, it goes below the x-axis and walks off in that way. Let me try to draw it a little bit better. So this does have symmetry with respect to origin. And now let's try this portion here in blue to see if we can detect it's odd just using algebra and nothing else. So first thing you'd want to do is just write down the left-hand side, f of x is the given function y, which is x cubed. Now we have to work out the right-hand side, negative of f at negative x. Our goal is to get x cubed back a second time, because if we can't, then this one wasn't an odd function and something on the paper is a lie. Maybe the formula, for example. So let's try the second portion where the red dot is. Negative of f of negative x. That's a tricky evaluation. First thing you want to do is copy that negative sign. There it is, it's copied. Next thing you have to do is look up the f function. It's this one right here. Takes an input, raises it to power 3, go back to f at negative x. Negative x would go inside there in just that way. So looking at this all together, negative x times negative x times negative x, that's negative x cubed, multiplied by negative 1, the whole thing turns into positive x cubed. Does that make sense to folks on the cancellation of those signs? Awesome. One way you can think of it is a negative times a negative has to return a positive value there. So I had 2 negative signs on this one. Here I have 3 negative signs because of the power, but then a 4th, so I should be getting a positive result, just x cubed right back. So these match up. That means this was true. We are dealing with the odd function. Let's just state the conclusion right here. This shows f is odd. So we have 2 ways to detect this, either visually or what we're about to do in example 6. We'll try it out purely using these 2 ideas highlighted in blue. Well, that's the main takeaways with even and odd functions. Honestly, it's kind of a weird concept because we already know about symmetry with y-axis. We already know about symmetry with x-axis. Essentially, the only thing that's new here is symmetry about the origin, where you flip across y and then the x-axis. But the ideas with even functions, odd functions, the reasons presented here is it does come up again and again and again in other math classes. So we won't do much with it. It's really mostly for homework. That's kind of a hint. It's not on the exam. Think of it as real good practice, but it makes a difference if you're taking more and more math classes. Let's give this a try. This is a typical problem you'll see in ALEKS. All they're going to say is determine if the function is even, odd, or neither. And that's our function to start off. That's tough, but sometimes it's good to have kind of a gut feeling about it, and we'll see if it works out or not. Any volunteers for what your gut tells you? Is that even or odd or neither? Some say even. I would agree with that. And the power 2 is a pretty good giveaway. If this wasn't ALEKS, you could also do this. Pick up your favorite graphing calculator. They're not allowed on exams, unfortunately, but no one's going to prevent you from pulling up anything to graph on for your homework purposes. It's always a good idea. Let's type in g of x equals sqrt, pulls up a square root, 49 plus x squared. And it disappeared, but hang on, let's zoom out. Yeah, I agree with everyone. That looks absolutely even because you can reflect it across the y-axis. So the problem is essentially done, but let's do it the hard way by looking at the original equations here and see if we can prove it's even. Yeah, go ahead.
So like with the graphs of where it is either it's just a line going on or that usually is like.
Are you saying like
square
this one
root of
here?
x. Yeah.
Yeah,
And so, but is it not that way because the x in this square root is squared, so it kind of eliminates. the
it does,
square root,
yeah.
and you end up squaring 49 in the process.
Well, we don't really square 49, but what's happening with this one is you can't put in a negative number in the root. You'd be taking the square root of, say, -1. Let's try it right here. And you would get undefined. It really is defined, but it's not a real number. So he'd say undefined here. But that power 2 means there's no problem. X squared is always positive, no matter what x you put in. Put in -20, and that's totally fine. You're just going to get -20 squared plus 49 and all of that square rooted. Does that make sense with the issue on this one?
I think so.
Awesome. So change one little weird thing on the function and you've got problems like on this right here, or you don't. The domain is all real numbers on this one. And just for fun, let's see what happens if you put a power 3 on that. Really strange, right? It ends right here. I can't put anything smaller like, say, negative, what would that be? -4 can't go in there because that whole thing would turn out negative altogether. So even non-functions are definitely weird. And this one is extra weird. Its domain is all real numbers, and we suspect it's an even function as well. Other questions so far? Okay, well, here's our major test. The function is even if g of x is equal to g of -x. Writing down g of x once, I mean, that's kind of silly. It's already here, so that's optional. But it doesn't harm us. Our goal is to try to get this back once we do that evaluation right here. So we'll go back to the g function. It's the root of 49 plus a quantity that is where x will go raised to power 2. And then this -x goes right into that placeholder right there. So once we simplify that, it's kind of what we did up above in the notes. -x times -x is just x squared with a positive sign. This returns root 49 plus x squared. Last thing we do is make a comparison. Here's g of x, the original function. Here's one where we calculated g of -x. And finally, we have a conclusion. G is even since g of x is equal to g of -x. So that's what finally finishes off this problem right here. Any questions, folks, on this one? Okay, to me, this is definitely kind of tricky. It's way, way easier to just look at a graph. This one's neither even nor odd. But if we put a power 2 on it, visually we can tell right away it's even. But the reason this is valuable, this kind of work, is it is plausible that someone's constructed a function that's so messed up that that looks like it's at the same height of this, but it's actually off by a tiny, tiny amount. You could build such a function, it looks even visually, but it's absolutely not even whatsoever. The only way you could detect it is using the formulas right here from scratch. So the algebraic approach has value. Essentially, all we did was check that equation out for our new function here. Now let's try it out again for f of x in part B. Well, any questions, folks, before we try a new one? Okay, it comes with uppercase F for no apparent reason. Sometimes our author just likes to give us different versions of naming the function. There's a power 5 here, so already I'd be thinking probably odd. Maybe, we'll have to check it out. There's also an absolute value function down below, plus 2. And, well, if we want to get a graph, we could do that right away. But how about we go blind and check our work after? Let's see what happens once we run through this problem. So we want to determine if it's even, odd, or neither. If we have no idea what is going to be, which is going to be which, here's what I would calculate to start off. Take a look at f of x. I'm really just copying, but it gets us started. It gets us warmed up. So there's f of x. If I suspect that this function is, say, even, I would be calculating f of negative x right there, because that's our formula from above in the notes. But if you think it might be odd because of your power 5, don't calculate f of negative x. Go up to here, calculate negative of f of negative x. That's what's going to show if it's odd or not. So negative f of negative x will be what we calculate right here. And I kind of meant for these to be in blue. Let's just fix it real quick. There we go, they're in blue. Well, we'll start off by just carrying a negative sign like before. There it is. Then when you see the function f, put it in with placeholders where x occurs. So there's a value of x in the numerator. There's x here containing the absolute value symbol. Last thing, throw in your negative x in those two containers. So we'll go here, raised to power 5, and here, where we take the absolute value. Well, we're just about there. Now this has to be simplified. Sorry, question first? The negative f right here. This one, oh, yeah, I did flip the sign. Thanks for spotting that. Let me go through this one more time. Really good eye on that. It took me a moment to even see it. So I started by copying that negative like you mentioned. It came from right, no, that one's new. I was about to make my same mistake. Let me use a parenthesis just to be extra careful on this one. There was an additional negative sign right here. Thanks again for spotting that one. Highlight that in yellow. Then I'll do the rest of the function. Does that make sense to folks where that missing negative sign was found to be? Awesome. Now for the rest of it, same strategy. We'll raise the numerator to power 5, throw a negative x in there. Absolute value of negative x plus 2. And I think we're in better shape now with that correction. I'll leave that highlighted in yellow to show where that negative sign came from. Then, like you said, there's a cancellation right away. So these two negative signs are just going to cancel out. I'll do it like that on paper, so it's not too messy if you come back to read it. However, from here, when we take negative x to power 5, there is 5 negative signs, so we still get a negative, and then x power 5 in that way. But does that make sense to folks going from here to here? Okay, awesome. Then down below, not as bad. When we take the absolute value of negative x, that just becomes absolute value of x itself. The negative sign gets wiped out. We get a plus 2. And let's check this out. When we did negative of f of negative x, we get negative x power 5 divided by absolute value x plus 2. We have the same thing right here. Only difference is the position of the negative sign, but you could throw it right here into the numerator if you really wanted to. So at this stage, we can say I'll put three little dots in a triangle arrangement, just a way to say, therefore, or in conclusion by this work, f of x equals negative f of negative x. And so f is odd. So we have an odd function, but we can also test this out in Desmos if we want a really fast check. Should we check it out? Okay, let's see what it looks like. Why not? So that was a strange function there. This next one's going to be even stranger. F of x, first that negative sign, then a fraction, x power 5 above, then, oh, and then down below, absolute value of x plus 2 gives us this graph. It's really hard to see what's going on. Let's zoom in on it. But yeah, that looks like we have symmetry about origin on this one. You can reflect once, the line would go here, reflect again, it would go there, overlapping. And the one down below, after the two reflections, would overlap with this line as well. So we really are looking at an odd function, and that's the verification right here. Well, any questions, folks, on this one? Okay, that's the wild world of even and odd functions. Probably another reason that people like this kind of stuff is, here's another takeaway when it comes to even and odd functions. Last thought, and then we'll go to the 3.7 notes. So the last thought I want to put on here is, there's another way to think about all of this. There's so many points of view you can come at, but if you see a negative sign right there, that is a reflection across, anyone recall which axis? The x-axis or the y-axis? Good call, that is a y-axis reflection. Then if you put a negative sign right here, that one is the x-axis reflection. And so we're saying if you have an odd function, it's symmetric about the origin, because if you reflect across the y-axis and you reflect across the x-axis all at once, you get the original function. That's what the equality there is indicating. So that's another way to think of these if it's helpful. It's a great way because it ties together those other topics about reflections. I think we've kind of killed these notes. Any last questions, folks, or comments before we jump to section 3.7? Okay, let me save this up. And now we're on the last section before our upcoming exam. So we're definitely getting through it, folks. So let me show you kind of the organization of what's going to go down on these notes. First thing we have to talk about is a horizontal line test. The problems on these are always kind of fun. They're really quick. There's not a lot of fuss on them. Reason why we care about horizontal line test is if your function passes the horizontal line test, it becomes an invertible function. So we'll see what it means for a function to be invertible just by the graph. But we also know we can't always rely on the graphs. Sometimes you're just given a formula and nothing else. So think of horizontal line test as a test for invertibility. But if your functions look like this is what it looks algebraically. So if your function passes these two composition tests, you get x both times. It turns out that the function g was the inverse of f that we're going to write in that way. So we'll spend some time practicing it this way as well. This is a little bit trickier. And then finally, we'll see how to plot an inverse function based on its graph and how to actually come up with the function inverse based off just one function here. So that's going to be our goal. And I would say these last two questions, I'm going to adapt one to be the quiz before the exam. So that would be a great one to have solved and ready to go before the exam number 1. I'd say example 6 or example 5 are going to turn into great exam questions. Let's go to the very top and give this all a try. First, I put this here really just as a reminder. The moment you sketch a curve on the XY plane, that will be the graph of a function as long as a vertical line intersects your graph at most once at any vertical line you put on there. So it says here on example 1, for each function graph below, well, already they have to pass the vertical line test because the author called them functions. Let's take a quick look. Yeah, it looks like it does in fact pass the vertical line test. We really do have functions. Now this is the portion that's actually new. If we have a function that is 1-to-1, this will happen if and only if every horizontal line intersects the graph of f in at most one point. So looking through all these, the horizontal line test is going to pass just about all of them. But anyone see a graph number where a horizontal line test would fail? Yeah, go ahead. Definitely graph 5 is looking really bad. That looks like some kind of weird sine wave of some kind. But this one is an absolute no, it does not pass. If we draw a vertical line, well, that one's no good to us. It didn't intersect at all. If we draw a different vertical line, say this one, it's intersected in 2 locations. That means, no, it's not 1-to-1, because we get to the height here about 2 more than one way. You can get it from this location or from that location. So that one's a no. And looking at this one, graph 4 has a problem as well. Would you all agree? So this one fails. Even though they're functions, they're not 1-to-1. And if your function is not 1-to-1, we cannot invert it. So these are non-invertible functions altogether. But the rest of these, yeah, any horizontal line you draw through there will only intersect once. That one looks linear, so it will have an inverse. Same for, say, this one. And they can try to get tricky with us, but any horizontal line you draw will only intersect once, no matter how many lines you put on there. So that one is also 1-to-1. And the only way this one would be a problem is if they put an extra point, say, maybe right here. If they did that, well, one horizontal line can go through 2 points, so it would have been a no. Let's correct that graph. This one is going to be a yes, because every horizontal line you draw is only going to intersect 1 point on this disconnected graph right here. So that's the gist of the horizontal line test. Any questions at the moment, folks? Okay, so what this finally tells us is if y equals f of x is a function, then, well, the whole section at 3.7 is inverse functions. We'll say y equals f inverse of x is its inverse, provided it passes, this is a longer sentence than I anticipated, the horizontal, I'll write H for horizontal, line test. So everywhere we said no, those are going to be the non-invertible functions. Everywhere we said yes, these functions will have an inverse. And we'll find inverses to some of these kinds of functions on these notes. Well, any questions at all, folks, with just the visual test for invertibility? That's a nasty word. Okay, let's go off to, well, I kind of talked through this. We should talk through it as well. All that was saying here on this theorem is if you have a invertible function, then it must be 1-to-1. And so the big takeaway is if you pass the horizontal line test, the inverse will exist. Well, again, we kind of talked through that on the notes right here. But what if we don't have a graph? That's when we're going to be doing this definition here. This is really the core definition for what it means to have a function inverse. And it comes with interesting parts. So let's walk our way through this. We have 2 functions, f and g. Now, at the end of the day, we're going to say g equals f inverse, but only if it passes our test for invertibility that's baked into the definition. Next thing you have to watch out for is the compositions. We have f of g of x, and we have g of f of x, but that doesn't tell you the formula for the composition, so always keep this in mind. F of g at x really means f evaluated at g of x. So that's what really goes right here, if you want the formula just thrown right in. Likewise for this one, g of f at x, really means take G and throw the function f of x inside of it. So a function inverse means no matter how you compose the functions, you get the same thing out. And not just any the same thing, we're going to be getting x itself back. But this is only going to be for x in the domain of G on the first composition. That has to make sense because that's where this x is going. It goes through G first. On the second row, this is for all x in the domain of f. And again, that's because x runs through f first. So we have to think of the domains in that kind of way. So if f and g are both invertible, because these two things held, we'll write g is the inverse of f. And this is the big takeaway. We'll have that property there. G equals f inverse. Now in mathematics, invertible functions become extremely important. We're going to see them come together once we start looking at exponential functions. The inverse of an exponential is a logarithm, and that's kind of the reason we're talking about inverse functions right away. Plus, if you're doing trig, you'll do sine, cosine, tangents, the reciprocals. But all of those trigonometric functions, there's 6 of them, they have inverses. So you have to study the inverses as well as the original functions in a trigonometry course. So this kind of content, the short of it is, it's another set of topics that keep coming back quite a lot. Well, that's how the definition goes. In example 2, we're going to do a really fast problem. You'll see this one in Alex. It's tricky at first, but it kind of explains why the definition goes this way and what the objective even is for an inverse function. It's really about equation solving more often than not. Then example 3, we'll test if the two functions are invertible and go from there. So first, let's hide that one. Example 2 is a really tricky problem, unless you're thinking of this definition as you go to solve it. We have a function and we don't know much about it except f of 9 is -3. But we also happen to know f, actually let me use this color, f is an invertible function. If it has an inverse, we'll write this out right away. F inverse exists. That deserves an exclamation mark because not every function has an inverse. All it has to do is fail the horizontal line test. Now here's the objective. We want to calculate f inverse of 3. It's actually pretty fast. Anyone happen to know what it would be? Here's a really interesting takeaway also with inverse functions. When you see f of 9 equals -3, it means 9, -3 is on the graph. Oh geez, I pressed something I shouldn't have. There we go. Graph of f. Now, the big takeaway with inverse functions is all they do is they switch input and output. So -3, 9 is on the graph. Oh geez, did that again. Let me just fix this. Is on the graph of the inverse function, f inverse. So that's what's going to happen with this value here. That means f inverse of, there is a typo here. Let me fix that right away. Sorry for anyone who's printed this out. That should have been a negative sign right there. Only just detected it. Let me put the whole thing in red. So we're going to evaluate f inverse of -3, and with that correction, the whole thing just comes out as a 9. That's really our answer right there. So this gave us an ordered pair, 9, -3. When you go to the inverse function, it swaps the x's and the y's on every single ordered pair. So that means 9 should be the result. That's one way to do it if you like points. Let's write it out as an equation. So this would be my official answer of how I would typically solve this. Let's first write f of 9 equals -3. So that's our first step. Now recall, if you're solving the equation, you are allowed to do one thing to the left-hand side and that exact same thing to the right-hand side. And the thing I'm going to do is apply the inverse function to both sides at once. So we'll go like this. On the left, I'm going to take f inverse of f at 9. On the right-hand side, take f inverse of just the -3. So let's take a look at this portion, f inverse of f at 9. Going back to the notes here, if G is f inverse, these compositions, every one of them, no matter the order, results in a type of cancellation. There's a 9 right there, you just get a 9 right back. Or if you're looking at it in this form, the f with G, they cancel like that. They're just gone if they're really inverse functions. Or G with f, same kind of thing. So inverse functions are a form of wonderful cancellations that we'll be using and abusing once we deal with exponents and logarithm functions. Down below here, cancellation goes just like this, and we can explain since f inverse exists. It will automatically just destroy the f function right here. In other words, whatever f did to 9, the inverse completely undoes it and brings you back 9 via original input. So we'll get a 9 back right here equals f inverse of -3. I'll put a box here to signify that would be my official answer in this process. If you know the trick of just switching the point, then that was the answer right here as well. Not the whole point, just the 9 is the answer we're expecting. So the short of it is, if f of 9 is -3, f inverse of -3 just brings you back the 9 that we started with. Any questions about that so far, folks? Okay, so that's the value of these kinds of equations right here. What they're really trying to do is give us a framework so that if you have a function you don't like, maybe it's a tough exponential, you can use an inverse function, as possibly a logarithm, to wipe it out and still solve the equation like we see here. That's the analogy we're going to be using, and it'll be the things that we actually do once we get to exponentials and logarithms. But first, we ought to practice with this definition once again. We're just going to take a quick screenshot. And here's the second version of problems we'll see in this homework. This homework is kind of short as far as this section goes. There are 7 different topics. Some of the problems are quicker like this one, or even quicker like these. These were probably my favorite. But some of them are a little bit longer, and this is the little bit longer type of problem. So I'll just put this definition here just for a quick reference. And now let's try it all again. Now our goal in this problem is we just have 2 functions. Here's a f function and a g function. And we want to know if they are inverse to each other. So it's not showing how to find the inverse. That'll be the last part of the notes. Sorry, say again. Yeah, you could calculate the inverse of your f, show it that it's g, and that would be a very fine way to do it as well. That's what we're going to be doing in these examples down below. We're just going to calculate the inverse straight out. And if you know how to calculate the inverse, that's a great way to solve it as well. We're kind of building up to it. So I'm going to do the problem by just doing these 2 evaluations and see if it tests as true. We get x both times, but your solution does work great. Other questions, folks, before we try it out? Okay, so we have 2 functions, and all we're trying to determine is that function g really equal to f inverse, like what's highlighted here in purple? All we have to do is run through the compositions, but notice there is 2 different versions. Now, if it tests and gives you x on one, there's a really strong numerical evidence you'll get x on the second one, but that is by no means a guarantee. Our book actually mentions this, that, well, they got x the first time they try, so they don't have to do it a second time. That's true for the problem that they did, but we can invent problems where that breaks down. The best method is to try it both ways and see if you do get x both times. That's the gold standard to know for sure nothing tricky is going on with the function. So I'll start with row 1. First, let me color code functions. For some reason, I like f in blue, g in green, no apparent reason. I'll start on this line right here, f of g at x. It becomes the function f evaluated at g of x. So honestly, if you wrote this much just to start off the problem, that'd be completely fine. Our author sometimes emphasizes this, and that's why the formula is written in this way. But really, I started here, and now I'm going to be making the substitutions. So going to the right, we now have f at the function g of x is just x plus 3 divided by 7. Next, on our second substitution, the function f goes 7 times some input minus 3. And the input we're throwing in is just a x plus 3 over 7. So at this stage, remember our goal is to get just x back. If they really are inverses, things should cancel some way somehow to return an x. But if it's impossible, if there's no way we're getting x back, then we just say they are not inverses to each other. But it looks like we do have cancellations. This 7 can cancel into that 7 down below. Upon doing that, all that's left is the x plus 3 in the numerator minus 3. We do get x back. As that says, they're probably inverse functions, but it has to work the second way as well. So we need to check out g of f of x, see what happens in that location as well. Well, any questions so far, folks, with that composition? Okay, so inverse functions, honestly, they sound scary. There's a lot of weird things going on, but if you feel comfortable with horizontal line test, and if you feel comfortable with this kind of composition, then you're in great shape for the exam. This is really just reviewing function composition in a big way with additional information about what you're getting as a result, inverse function or not. So think of this as really a kind of review. Now let's try it again. We need to know what g of f at x evaluates to. Now, these are always tricky. The order makes a big difference. First, it's going to be the g function. And we're throwing inside there f of x. Then this becomes g of, looking up f of x, that's just a 7x minus 3 going inside g. Finally, next substitution, this becomes methodical after a while. Look up g, it's the function that goes like this. And input x plus 3 divide by 7. Then that input is going to go into the only open parentheses we put in, 7x minus 3. And from here, we're just canceling and simplifying. Parentheses here could be dropped right away so that this negative 3 and this positive 3 are an immediate cancellation. Then you get 7x over 7. Here's our next cancellation. The 7s are just gone. And we get x back. So that's great. We found f of g of x is x, and g of f of x is also x. In other words, we do have a pair of inverse functions, but this is kind of a tricky problem because there's one additional thing to do. It's small, but anyone see what it is? Yeah, go ahead. Good call. I mean, that's so easy to forget, but if what these instructions say, determine if the functions are inverse to each other, this is not enough. I need to know that you know that all this means g is f inverse. So good call. I think the trickiest and easiest thing to miss here is the conclusion. So let's put it just a quick note. Don't forget the conclusion. Because we got x back both times, I wrote equals right here. And if just one of the equations gets messed up, and we don't get x back, or we get domain issues, we would put not equals right there as our end conclusion. So that's running through this process. And for the next problem, we'll just practice it again. Any questions at all, folks, on testing for invertibility? Okay, and like was mentioned earlier, the way I did this problem wasn't by finding the inverse of f, but that absolutely does work. This is kind of a frustrating problem in a certain sense. It's only testing if the functions are inverse to each other. But when we do example 5, we'll be actually finding the inverse of those given functions there. Well, let's try this again with part B. I have a quadratic function p of x. This one we'll call later on a rational function because there's a polynomial in the denominator. And the reason I posted this problem is because of small matters when it comes to that symbol right there. Let's actually make a big deal out of that before we get going to the next problem. If you write F inverse, then that right there is not an exponent, which is kind of frustrating. We expect it to be, but it's just a way to say you have an inverse function. The whole thing is just read as F inverse altogether. Now, what that means now is if you see this function that just got thrown down in the denominator, it does have this analogy that 5 to a negative exponent is 1/5. But over here, this one is an exponent. To me, that's really very tricky. Numerically, these kinds of things are indicating exponents, and it's just saying divide by 5. But over here, that is not the case. So if you see a whole function thrown into the denominator, I mean, they might be inverses, but it might be Alex is trying to see if we have indicated or saw this issue, that it's not an exponent at all, and simply tossing stuff to a denominator does not necessarily give you an inverse function. So that's a takeaway on part B. Now let's test this out. If it is an inverse function, both of these have to be satisfied. Sorry, go ahead. Exactly. As soon as you have an even function, actually because of this, it may not be even, but it's very close to it. Let's actually go to the graph to connect that thought. If it looks like this, P of x equals x squared, right away it's an even function, which would mean doesn't pass the horizontal line test, right? Which would mean automatically there is no inverse to this function at all. So I like the way you think about this one. If you have a feel for what the graph looks like, then you can tell immediately if you can invert it. If you put in the negative 6x, the whole function, it still has symmetry, but the symmetry would be about the vertex right here. It's not even because it's not reflected across the y-axis symmetry, but still same issue. It fails the horizontal line test just immediately. So this one cannot possibly be a pair of invertible functions. P of x on its own has no inverse. So that's a great way to think about these kinds of problems. Other questions at the moment? Okay, let me put this on our notes right here. We can say, since P of x does not pass the horizontal line test, it has no inverse. That deserves an exclamation mark, since if you're thinking geometrically like that, this problem analysis is like instantly done, right? There's nothing you had to do to it. You would just write as a conclusion immediately that Q is not equal to P inverse and vice versa, because they have no inverses, one to the other. Well, other questions so far? Okay, this is doing it all graphically, which can be tricky unless you have a good feel for what the graph should look like. But if we were going to do it algebraically, we have to run through those two kinds of compositions. So let's give it a try just to see it from that point of view, algebraically versus geometrically. I'll first do the f of g of x. Think of P as being the f and Q as being the g. I mean, it almost looks like g. So to start off, I'll write P of Q at x. Let me also color code. P will be blue, Q will be green. Then if we do this composition, we're going to take a P function, throw inside there Q of x. I made those parentheses rather big. I think I was about to skip a step and just put 1 over x squared minus 6x inside there. If you're skipping that step, I'd say good on you. You must have done lots of compositions, and so you're getting very fluent with it. But here's my extra step, 1 over x squared minus 6x. And I forgot to highlight the P, but we can always just do that in that kind of lazy way. Then go back to the P function. It takes the square of something minus 6 times something. No matter what your something happened to be, and this time it's this. 1 over x squared minus 6x, 1 over x squared minus 6x. So that's our function. And if they were inverses, somehow, some way, all of that has to equal x. Well, we can do some algebra on it, but no matter how much algebra on this we do, would you agree it's probably impossible this equals x? I would agree with that assessment here. So how about, I would say here, if this was on a quiz, oh, that was meant to be a different color. If you stop here, because maybe you saw the graph and you knew P had no inverse for the first place, or because you saw this and you knew it does not equal x. After simplifying, I would always consider that to be full credit, whether you're in a quiz setting or an exam setting. If you get to this and you know that's not working out to x and you just conclude Q is not P inverse, I would be happy with that. That's kind of the takeaway with these problems, trying to simplify to x and knowing when it's never going to happen. But I'll leave it up to the class. Should we keep going and try to simplify, or do folks feel okay with where it sits right here? Any volunteers one way or another? Okay, thanks for making that determination there. We'll leave it just like this. If you were to try to keep on simplifying, you would have 1 over that whole denominator squared. That matches with this one. Now you have to find the least common denominator, subtract across numerators. It just becomes a giant mess. So that becomes a really strong takeaway. If you know it can't equal x, you're welcome to stop. Or if you know it couldn't even pass the horizontal line test, you don't even really have to do this at all. Just make that as a comment. This is a power 2. It's going to fail the horizontal line test immediately. Well, last thing on the table for us is let's try out one more matter. So far, we know what an inverse function looks like, passes a horizontal line test. For given an equation, we just have to do 2 function compositions to determine if one's inverse to another. But another thing we might do is, if you're given a graph, well, that will pass the horizontal line test. We have to know how to produce the graph of the inverse. So let's try that as our next problem. As we go through this problem, this theorem is really just a collection of all the properties of inverse functions. This is the major one. If you plot 2 functions, f and its inverse, on the same set of axes, they will be symmetric across a line y equals x. But symmetry across a line y equals x goes to a different matter we talked about. If a point xy, or AB, is on the graph of f of x, then that symmetry across y equals x means BA is also on the graph of the inverse, which is what we want to plot on this one. We'll return to these other 2 properties next, but this is enough, property 1, to graph the inverse of that function there. So it says that's the entire graph of f. Graph its inverse on the same set of axes. And actually, it's not too bad. Let's just grab all of our coordinates. Here, this is going to be the coordinate of 5 and 3. Down to this coordinate, we have, let me know if I miss a coordinate. This one looks like 3, -3. Then last coordinate here, looks like I have a -7 and -5. Okay, I'm going to try and keep the inverse in purple just to make it pop out. So now when we go to graph the inverse, we take all these points and just flip the coordinates on them. So I'll indicate that this way. I'm going to transform to f inverse and get 3, 5. And that's pretty much it. Just interchange your x's and y's. Let's throw it on the graph. 3, 5 goes 3 here, all the way up to 5. So that's the first point. And as we plot these, keep in mind, that's the major portion of the theorem. Everything else is really just a consequence, part 1, 2, and 3. So if it looks like you have a reflection across y equals x, then keep on going. It means you're definitely on the right track. So there's the line y equals x, and yeah, it looks like it reflected across. Let me try maybe plotting that line just a little bit more clean. Y equals x would be more, oh dear, let me try again. It'd be more like this. Kind of bent it, but you don't have to have perfection. So there's my line, and yeah, if you fold the paper across this line, that purple dot lines up. Let's do it again, -3 to -3. If we're going to the inverse graph, that'll be -3, 3. So here's -3, up 3, goes about right here. So yeah, this point reflected across y equals x, ending up in that location. And one more time. This point, when we transform it to get f inverse's graph, becomes -5, -7. So here we are at -5 down to -7. Oh, didn't need to draw on it. Would be about there. Oh boy, my line on this end looks a little bit messed up. Let me see if I can correct it. So it should go down like that. It looks a little bit better now. Yeah, this reflected across in that way. Once I corrected my line, I should have plotted y equals x a little bit more carefully. But now we just connect the dots in purple and not delete them. Let me try again. So from here to here, this is y equals f inverse of x. So really pretty fast problem. All you had to do is just swap your points and you have the inverse graph. Any questions about that so far, folks? Okay, so there's a little bit more to the takeaway on this theorem we're saying here. If you have to find the domain of f inverse, it's actually not so bad. It's the range of f of x. And likewise, the range of f inverse is the domain of f of x. So if you know the domain of this function, f of x, the domain of f would be, let's see, goes from -7 all the way to 5. That'll be with brackets. Then that's enough information for you to find the range of f inverse, just the domain of f of x. So let's say here, range f inverse should be -7 up to 5. And that was a bracket right here. Let's check that out if it really works. Range goes down from -7 all the way up to 5. It really lines up. Then last thought, we say take the range of f. That's the original function here. Its extent on the vertical axis goes from -5 all the way to +5. But that means, once again, if you ever needed the domain of f inverse, you just had to know what the range of f of x is. So let's indicate that here. Domain f inverse equals, says pick up the range of f of x. We indicated right here, it should be -5 to +5. But let's check that out. On purple, the extent on the horizontal axis starts at -5, goes all the way up to +5. So yeah, we do have this weird switching of domain and range. We'll take strong advantage of this on some of the problems coming up next. I think this is probably a really good stopping point for us. Really, the whole thing that answered the question was this table of points and this curve going here to here. Everything in orange and the domain ranges was just extra, so we could analyze the theorem here. Well, any last questions or comments, folks, before we call it a day? Okay, when we come back, there's really not a whole lot left on this. We'll do examples 5 and 6. They are a little bit longer. They'll be similar to the quiz. And we will have finished off everything about inverse functions. At that point, I want to switch over to just taking whatever few questions you might have. If you run out of questions, I'll bring some of mine own as well, so that we'll have a good, decent review to end the day on. Well, have a great day, folks, and I'll see you all in Thursday's class. Sorry, say again. Oh yeah, that is a wild function. I can see why it would. Let me see what it will do on my end, so I can see what you're looking at. Y equals x to power x. Yeah, I can see why it doesn't have a negative domain. Let me see how it came out on yours. Oh, it just has S yet, so it grabbed something slightly different. That's really cool. Yeah, I started up with a y equal to force it to come out as a function. Big question?
Yeah, when scheduling the test with my testing center.
Mhm.
Does it have to be at the exact class time?
No, it
Or
doesn't.
can I like do it in the morning?
Yeah, it's gonna be up to you. And I mean, their schedule too, but usually they have a pretty wide open schedule. So yeah, it doesn't have to be at the exact time.
Because sometimes between my husband and I schedule, there's
Mhm.
conflict and apparently on this time next week, he needs to go arrest somebody.
I see, yeah. Oh,
It's like,
dear.
please let me know ahead of time.
Yeah. Bad day for that guy, but not too bad for you if you got that planned around.
I'll make poor decisions, that's what happens.
Absolutely.
So, but I need to check, because I feel to accommodate what he needs to do, if I could. I would just take it in the morning after I drop kids off at school.
Yeah, that will work just fine. And sorry for the confusion. It was on Monday. It's supposed to be on Tuesday.
Okay, yeah, that's what I thought. So is that pretty much the case for all of our tests? They're on Tuesdays?
Yes, our final
Except for
is
the
on a
final.
Monday. Yeah, that's the only exception.
Okay,
Yeah. And if there's ever like a
'Cause-
conflict with them and they say, sorry, Tuesday's booked, you have to do it on Wednesday, that's okay. We just have to work within what their availability is too.
okay. Because I didn't do it this semester, but like last semester I was really good. Like at the beginning of the semester, I just scheduled all my tests.
Mhm.
'Cause they were, like,
You're
they were
welcome to do
giving me
that if you like.
advance.
Yeah,
They were pretty good about that.
awesome.
Alrighty, well, I guess I'll see you shortly.
Sounds good. I'll be there in not too long.
Sounds good. Thanks.
Mhm.